I want to hit one sort of quick point. So what I think is kind of the key, the main idea behind ferrite, and because I managed to confuse myself last Friday, I want to reiterate. I thought I was hit it pretty clearly in the recorded lecture, but I want to hit it again real fast. And that it's perlite colony, right? We've got a couple different ways we can grow, right? We can add new layers growing along the austenite grain boundaries. We can grow by making the existing laths longer, right? Or we can branch, right? And growth by making it longer is basically the same as the growth of the other ferrite structures that we talked about. The lateral growth along the grain boundary occurs by what we called sympathetic sideways nucleation, right? And this is, imagine we're growing a ferrite lath. We have to partition the carbon out. So basically we have this diffusion field of an enriched carbon region out front of the lath. And eventually this will get high enough that it will nucleate a new cementite lath. And the same thing over here, if we have cementite, we have to diffuse carbon into it, away from the austenite, and eventually we will drop down to a level that's low enough to nucleate a new ferrite lath, right? And provided the temperature remains constant, that's why we get this very regular spacing. And now the part that I managed to confuse myself about, because I don't know how to read a 1/over reciprocal graph, right? So if we think about what's going to happen at higher temperatures, right? At higher temperatures, we have less driving force for growth, right? And the closer we are to the eutectoid temperature, we're going to have less driving force for growth, but we're also going to have higher diffusivity, higher mobility, right? So that means this front is going to be moving slower, and this diffusion field is going to be able to get out of the, right? The diffusion is going to be faster, so the gradient won't be building up as much, right? So that means that we're going to have a wider lath spacing than at lower temperatures, simply because we're not going to be building up the carbon as much, right? And right, this is, so I got to this graph, and suddenly on last Friday managed to get really confused, because my understanding of what I was seeing on the paper or seeing on the screen and my understanding of the physics clashed. But this is a reciprocal spacing, right? I even said it, right? That the linear relationship exists between the reciprocal of the spacing, right? So that means small reciprocal spacing means large regular spacing. And large reciprocal spacing means small spacing in the real. Yeah.
So did you just say when there's diffusion, then the diffusion is faster, and then it ends up being wider?
The lath becomes wider because it takes a longer time to get up to a carbon concentration.
And then in the online one, you said increased temperature slows down growth and lower interface.
Yeah, the interface itself is moving slower, so you're partitioning slower, but you're diffusing faster. So that means a wider spacing between nucleation events, right? And this is what I want to be really clear about, is because there's a lot going on and it's easy to get confused, right? Right. So, and specifically, it's a really important point. It's probably the most important point in all of this perlite section is what's going to determine the perlite structure, because the structure of the perlite is going to really influence the properties, right? Right, because the spacing is going to be directly related to the fracture toughness, to the hardening, the Hall Petch type effects that we see. So just keep that point in mind. Like I said, I hit it pretty hard in the yeah. I got to think about that. I don't believe so, but steel is weird, so I don't think so.
Okay, so it's always
Yeah. Okay. And so now we go on to Bainite, which is the least understood and most confusing steel structure that there basically is, right? It's not particularly well defined, right? Basically, it's something that's halfway in between perlite and martensite. It grows by a shear mechanism with diffusion. It's not, people still argue about what the actual mechanism for Bainite growth is, but basically it's these plates of ferrite that are separated by carbides, right? It's a not lamellar structure like perlite, right, where everything's nice and orderly, right? We've got plates with carbides in between, and then a whole bunch of dislocations in the ferrite. And these dislocations give us make Bainite much harder than the ferrite in perlite, right? So higher temperature, at higher temperatures we get the perlite reaction. If we go a little cooler from the perlite reaction, we may get Widmanstätten ferrite. If we go a little bit lower, we get Bainite, and if we go even lower, we get martensite. Right, so at these intermediate temps, roughly 250 to 550 C, we get these fine ferrite laths separated by carbides, and there's two structures. We've got upper Bainite and lower Bainite, right? So the primary difference is lower Bainite occurs at lower temperatures, right? And whereas and has a larger, right? In upper Bainite, you get more diffusion out of the laths, so the lath forms, or the plate forms, then you get diffusion of carbon out to form carbides, right? Whereas with lower Bainite, most of your carbides grow internal to the plates because the carbon doesn't diffuse out as much, right? So basically, intermediate isothermal holds, or as we'll see, if we cool fast enough, too fast for perlite to form, but not fast enough for martensite, we can get Bainite, right? And that's just sort of shown out on the TTT diagram. Yeah.
On the last slide, are those two micrographs same scale?
Probably not. Right, that just shows sort of the general morphology. Right. I don't know what the scale is on this one. You'll find what annoys me is a lot of texts ignore the rule that you're supposed to put scale bars and everything, and instead, like Reed Hill really annoys me because they say 350,000 magnification. Well, that's at the scale that it was printed in the book, right? As soon as you put it on the notes or resize it, that number is meaningless, right? Unless you know exactly how it was resized. But if we look at the isothermal TTT, the TTT diagram, you see the relationship we just said, right? There's the Widmanstätten. A little bit lower is our Bainite start temperature. We go lower still, and we get to the Martensite regime. But notice Martensite is this flat line, right? So it's athermal. It takes basically no time to form Martensite. Bainite is not athermal. It takes time. It has a measurable kinetics associated with it. So in that way, it's sort of like this hybrid in-between thing between Widmanstätten, Ferrite, and Martensite. And here, if we cool, you can look at our continuous cooling curve. Very fast cooling rates, we miss the nose of Bainite and we come down directly into the Martensite. If we have intermediate coolings, we come across Bainite. Slow coolings, we cross into the nose of the Ferrite and Perlite region. And you can see here, depending on how wide this is, we may completely go to Perlite, or we may cross into and get some Bainite as well. Right. And so this is a really nice figure I like from Harry Badisha. And basically, it shows that here's all of our reconstructive mechanisms. This is perlite and our idiomorphic and allotropomorphic ferrite up here. And down here is our sort of displacive mechanisms, Widmanstätten, Ferrite, Bainite. And you see this has got a really flat top, right? So that means there's just some temperature for a given steel that when we're above it, we're not going to actually be able to access any of the displace of any of the shear transformation mechanism. And we're going to be completely diffusion controlled. But that as the hardenability of our steel gets higher, right, these two curves tend to overlap, right? And we don't see this clear separation between the displacive and reconstructive mechanisms. Right, and when we specifically talk about hardenability of steel and heat treatments of steel, we'll come back to this figure. Right. But what I mentioned, as I mentioned before, this is a non-lamellar plate-like aggregate of ferrite. So we get these and especially upper Bainite, we get these ferrite laths with the carbides in between. And the important thing is the carbides are not essential, right? So the main thing with the Bainite reaction is the forming of the ferrites, and the carbides actually appear by diffusion later. And we can actually alloy with certain elements, combinations which will suppress the carbide formation. And so we can have Bainite that's composed of supersaturated ferrite, right? Much like making it even more like Martensite. So these individual plates are only about 0.2 microns thick. So that means we can't see the individual plates in optical microscopy, right? You can only see this, what we call a sheath of plates. Lower bainite, at lower temperatures, we have carbides that then form in the individual sheaths, individual plates. So now we get into the confusing part of bainite, right? So it has a dual nature, right? It has properties that are very typical of nucleation and growth, type reactions, and then an equal number of facets that would classify it as a purely shear type transformation like martensite. And but it involves compositional changes, so we still partition, right? And it requires the diffusion of carbon at some level, and this makes it very different than a typical martensitic transformation, right? And as I mentioned before, it's not a thermal, it requires time. So we get a S-shaped nucleation reaction curve, not nucleation curve, right? So if we look at this as the percentage of austenite transformed to bainite as a function of time, we get this sigmoidal shape, but that it might not go to completion, right? In fact, most of the time it doesn't go to completion. This schematic alloy, we're only going to about 80% bainite. And this is really typical of bainite. And the kinetics are not real clean. Doesn't follow typical JMAT kinetics at lower temperatures, right? So you can see these curves here are basically Avrami, which the assumptions are that the particles are basically, the nuclei are non-interacting, right? We have homogeneous nucleation, and all those things that go in. They're sort of okay at high temperatures, but at lower temperatures we see a distinct divergence from the kinetics from JMAC. And also notice the time scales of this can be pretty significant, right? This is iron 1.1% carbon, and at these lowest temperatures, right, we're taking 10 days before we're at fully transformed to bainite. And if we think about what happens with martensite, right, if you get into that martensite regime, right, it takes basically no time at all, right? So bainite is this confusing, monstrous mess. Okay. Like martensite, we have this bainite start temperature. And a bainite, there's a lot of books list a bainite finish temperature, but as we'll see, there's not a lot of physical meaning to that bainite finish temperature, right? It's not like a real thermodynamic temperature, right? So this is percent bainite formed. So it's somewhere between the bainite start and bainite finish temperatures, the reaction doesn't go to completion, right? So if the reaction doesn't go to completion, that means growth has to stop and nucleation has to stop, right? So what's the driving force to stop this, right? It's not, especially if we're still at a temperature, right, that's below the equilibrium austenite transformation temperature. So we're in an unstable austenite regime, but we still have a reaction that's not going to completion. So the reason, the reason growth stops isn't too difficult to understand, right? So either the Bainite plate can grow until it intersects another plate or an austenite grain boundary. That's one mechanism that can stop it. The other is that the growth of the Bainite plates can be limited by a loss of coherency between the ferrite and the plate and the parent austenite, right? So pretty simple and straightforward mechanisms to why growth stops. Why nucleation stops is a lot more complex, and we have to get more into the structure before we get there, right? So upper Bainite, right? So we see these subunits with the carbides in between. So we nucleate these ferrite plates, right? We have a invariant plane strain associated with this, just like with the Widmanstätten, right? We call these clusters sheaths, and these plates tend to be about parallel, and they all have relatively the same crystallographic orientation, right? With our and are separated by initially low angle grain boundaries, and then the cementite particles form. So these are approximately all the same orientations, right? And so these are just some images of the of upper Bainite, and I'm telling you, this stuff is hard to identify from optical, right? It's really difficult to tell Bainite from martensite from optical microscopy, and it wasn't really until the 1920s that people actually realized that this was a separate phase, right? So it grows at a higher temperature, and we know that there's a shear, a strain associated with it because we get surface relief, right? So if you have a polished surface, right, and you grow the Bainite, you get steps on the surface, right? And so, would someone have a question? Or is everyone? Right, so we get these steps on the surface, and then we'll get associated plastic deformation in the ferrite, and these plates are all significantly smaller than the prior austenite grain size. Right, so we have a displacive mechanism with diffusion accompanying, and we have a sort of Kurgyamov-Sachs relationship, right? You'll see this keeps coming up over and over and over again. Almost, but not quite exactly unlike Kurgyamov-Sachs, right? That's sort of like the big deal. The big thing with steels, right, is if there's an orientation relationship, it's going to be near Kurgyamov-Sachs. So because this has a shear associated with it, this is some atomic force microscopy, right? We can see the surface relief that happens, right? So it's not insignificant. So we get the shear, gives us a step on the surface. And unlike Widmanstätten, where we had two variants that had opposite shear growing next to each other to limit the strain, here our shear, right, initially the shear is going to be, you can think of it as a two-step process. We have the shear, which we then accommodate elastically, which gives us a big stress. Right now we've exceeded our yield stress of the material, and we have plastic deformation. So we've got an invariant plane strain shear here with plastic deformation over on this side. In reality, they happen at the same time, right? But you can think of it as a superposition of events, a two-step process. And this gives us this highly localized plastic deformation. This gives us a very high dislocation content in the in our bainite, right? Right. So that's the shear part, and then the formation of the subunits is then accompanied by diffusion of the carbon into the adjacent austenite. And when the carbon concentration reaches a critical value, the carbides will form, right? And they're not always cementite, right? We get a huge variety of potential carbides there. Yeah.
So in Martin said you can generally tell the curve, you have an idea of where your variance plane is. Right?
Yeah.
So, and you showed the figure before where you showed the bainite column dressing or bainite flat dressing, and then
Yeah.
the transformation into slip on the other side. Is that just the general structure of bainite, or is there no? Is that? I guess I want to think of it like Martin said, you have other kinds of service.
Yeah. Well, I mean, so in Martensite, you have to, we'll talk about it more, but Martensite is an exceptionally violent transformation too. There's a huge amount of plasticity, localized plasticity in the neighboring austenite, right? You have to accommodate all that shear somehow. So you do get plasticity with Martensite as well, but it's just the speed at which it happens, right? And if we go up to the next slide here, right? So here we've got bainite without aluminum, with enough aluminum and silicon, we can suppress the carbide formation, right? And honestly, if you just had this picture, it's impossible to tell whether that's bainite or martensite, right? You've got nice, clean, what looks like nice, clean laths, right? And so without the carbide separation, it really, there's so many similarities, except for the athermal nature of martensite, right? But basically, what we have is we have the lath forms, the plate forms, carbides diffuse out and form in between. So here's basically one sheath. These are the individual subunits with carbides in between. Right. Lower bainite is a little different, right? We have less extensive diffusion of carbon, right? So the carbides are going to form both between the ferrite laths and inside the individual ferrite substructure, right? And so the cementite that forms within the supersaturated ferrite, within the subunits, mimics perlite that grows from proeutectoid cementite on the existing cementite on the grain boundaries, and we get a Bagriatsky orientation relationship there, rather than the Kurgyumov sacks, right? So between the ferrite plates, we still have that low angle orientation relationship. We have a nearly common crystallographic orientation within the sheath, but between the carbide that's in the subunit and the ferrite that makes up the subunit, we have this orientation relationship that's observed, right? Right, and this is basically just the structure of lower Bainite. And that we often see the cementite of lower Bainite forms within these subunits with only one variant. Remember, these orientation relationships, because of the symmetries of them, you have multiple variants. So there can be multiple cementite orientations that have the same orientation relationship. And a lot of times with lower Bainite, we only see one, right? But occasionally, depending on exactly the things, so we'll see when we only have one, we have these nice parallel plates of cementite within the sublath. But we can nucleate multiple variants, and then we get carbide plates that exist at multiple angles, right? So you can imagine, right, if I have a different crystallographic orientation and I need to maintain the same interface relationship, that particle is going to appear at a different physical angle with respect to our cross section, right? So this is just more FYI. Most of the time this happens, but sometimes this happens, and we don't really know. We're not really sure why. Right? I think there are probably like 2 people on the planet who really understand Bainite. I mean, it's just incredibly difficult to study in any kind of cohesive manner. So this is from a paper, again, from Sir Harry Badisha. I think he's probably one of those 2 people. He did some really nice experimental work in the 70s and 80s and showed that the TTT diagram for Bainite is actually, there's 2 separate curves that intersect, one for upper Bainite and one for lower Bainite. And that basically he did this by a lot of very carefully controlled cooling rates, right? So that to come through here, and was able to, depending on how he hit the nose of this, go through a region where there was a certain amount of upper Bainite and then quench to martensite, right? But if he kept going, then he would hit into lower Bainite. And by doing a whole lot of really careful, experimentally controlled curves and quenches, was able to show that the kinetics of upper Bainite and lower Bainite are pretty different. And it's not just one continuum. In reality, you have to think of them as 2 separate transformations that their TTT diagrams intersect with each other. Okay, so that's structure. So now into the weirdness, right? So we still don't really have any agreement as to whether Bainite forms in a diffusionless manner or if there is diffusion that occurs during the transformation, right? So, and basically it says we don't know if in the formation of the individual subgrowth, if we have carbon partitioning or not, right? So you have the lath that forms, and then we know we have partitioning of the carbon after the lath forms, right? That's what forms the carbides. but we don't know if that happens, if there's also partitioning that occurs during the growth, right? So we know that carbon does partition into the austenite, right? It's really easy to establish this for martensite, right? Because martensite happens so quickly, we cool down, we get martensite, we can measure the composition before and after the transformation and see that the carbon content is exactly the same, right? Because we, at that point, are quenched down low enough that we can, that we know we're not going to have significant carbon diffusion. But since bainite forms at a higher temperature and the growth rate is not instantaneous, right? So the carbon can escape, and the plates are so small, the carbon can escape out of the plates in a fraction of a second or so, right? So we can't measure the original composition, right, at which it forms. We can only measure the composition after the cooling, right? So there's three situations that can happen, right? The carbon could have partitioned during growth, right? So that the ferrite never contains any excess carbon, right? That's one extreme, complete partitioning. The second is that it's diffusionless and the carbon is trapped by the interface and we have a completely supersaturated ferrite, which then diffuses out. Or it can be intermediate, right? Some carbon can diffuse with the remainder being trapped, and we only have a partially supersaturated ferrite matrix, right? And which of these is the case, we still don't really know, right? So we don't really understand what the precise role of carbon is during the bainite transformation, right? We know exactly the role it plays during martensite because we know where it is, right? So people have been able to figure out what's going on there. So if we look at diffusion-controlled versus diffusionless reaction models, right? There's a sort of the big controversy, right? I would say there's probably been more fist fights at metallurgy meetings or near fist fights about this, right? People still argue about it. And basically, if you look at the three different readings that I put up there, right? So you've got the chapter from Reed Hill, the notes from this course that were originally put together by now Professor Emeritus Glenn Merrick, right? That was actually, it was the notes from when this was just the ferrous metallurgy course. And some information on advanced high-strength steels. They all say that the evidence is pretty conclusive towards a different bainite formation mechanism. So they all claim that the evidence is on our side. It's diffusionless. It's diffusion first and then shear. It's shear first and then diffusion. Right? So I have my opinion, but my opinion means not very much. So I don't even know if I threw it in here. But if we think about it, if we assume that it is completely diffusion controlled, right? So that we have a non-lamellar eutectoid type reaction, right? It's basically just a non-lamellar pearlite structure, right? This is sort of going to one extreme. So we have this diffusion controlled growth along the edges, the ledges, Remember the step interfaces that we talked about with Widmanstadt and ferrite, right? We have that same mechanism at the austenite ferrite interface, and it's basically the same as Widmanstadt, and that the carbon concentration as the ferrite is very low, and we've diffused everything out into the austenite. So if we partition out into the austenite, we expect that's where the carbide should grow from, right? Because that's where the carbon is, right? Basically the same as nucleating cementite in pearlite, right? And so for upper bainite, we actually see that happening, right? People have done some careful microscopy and showed that the carbides do, in fact, precipitate on the austenite side. Except in lower bainite, they form in the ferrite. So we've got sort of a strike against the purely diffusional mechanism. Okay. So, yeah. Yeah, austenite. Yeah, so if you're partitioning carbon out of the ferrite, right, you're going to have an elevated carbon content on the austenite side. Right, just on the austenite side of the interface relative to the bulk carbon content. Right, because you're partitioning out, but it hasn't diffused away yet. So it's exactly analogous to the pearlite. So it starts on the austenite. That's where it nucleates. Right? It's basically just the same as the sympathetic sideways nucleation mechanism that we just went over in pearlite. Right? So diffusion controlled basically says that it behaves just like pearlite, but because it's at a lower temperature, it doesn't form this nice lamellar, beautiful structure. We get multiple little nucleation events, and it forms this lath plate messed up thing. Right, and it grows by, and the actual mechanism is invariant plane strain shear, like the like Widmanstadt. The diffusionless mechanism, right? This takes a little bit of understanding, so I'm going to start it, and then we're going to revisit this again on Monday, right? Because this is something I remember when I learned steel metallurgy, I didn't get at all, right? When I sat through this as a first-year graduate student, this didn't make any sense to me. And it wasn't until a couple years later that was like, oh, that's all it is, right? So we're going to hit this sort of a couple times here. So, okay, so the transformation needs, so let's create this is our carbon concentration. This is a combined graph. So this lower part of the graph, the y-axis is temperature. The upper part of the graph, this is free energy. So if we plot the free energy of our austenite and our ferrite phase. So for this to be happening at equilibrium, right, at a given carbon concentration, what does that imply about the free energy of the two phases? What's that? They have to be equal, right? There's no partitioning, right? So we need, so for a given carbon concentration, right, if our carbon concentration is here, the reaction is occurring where these two curves intersect, right, where they're where they're equal, right? And we call this, where they're equal, we call this the T0 curve. So if we plot the free energy curves for a range of different carbon contents and a range of different temperatures, and we look at where they intersect, right, this becomes the T0 curve, right? So this T0 curve shifts to higher values of carbon, higher percentages of carbon as our temperature goes down. Then we have two curves here, our equilibrium lines, right, which are basically given by the common tangent construction, right? So this is going to be the carbon concentration of the ferrite and the carbon concentration of the austenite, the retained austenite, if it goes to completion, right? And the T0 curve, by definition, sort of has to be in between them. Yeah. It's the equilibrium, right? So the chemical potential of the carbon is equal in both. The change in chemical potential is equal, is 0, right? Right? So don't get confused. What confused me is I kept expecting this to be a horizontal line, right? Saying that the equilibrium, this is what confused me when I was learning it, right? So that the tangent was a horizontal line, but that doesn't necessarily need to be true, right? It's just where the two curves intersect is the equilibrium, point. Okay. So if we increase the carbon content in the austenite from the T0 point, right, we're now at a position where our austenite has, at a given temperature, if we slightly perturb our carbon content higher than the carbon content for T0, our two free energies aren't equal anymore. The free energy of our austenite is lower than the free energy of our ferrite at that composition. So that means we can only, the reaction can only go forward with diffusion happening. It can't occur in a diffusionless manner anymore, right? And that's the key idea, right? That's the key idea I was missing as a student, and I think it's the key idea that I want you guys to get across, that if we're slightly to the right here, if we're slightly to the right here, we now have a delta between the ferrite curve and the austenite curve, right? Whereas if we're slightly to the left of T0, right, we can lower our free energy by going from austenite to ferrite without partitioning. But if we're to the right of it, we raise our free energy locally without partitioning. So we need diffusion for it to happen if we're to the right of it. Okay? So what does that mean? It means basically if we're at a composition at a given temperature, right, we're only going to create bainite, right? So we make the plate, then we diffuse carbon out, right? And now the next plate has to nucleate in a carbon-enhanced environment, right? So it'll nucleate, and it'll still reject more carbon. So every plate we nucleate, we're building up more and more carbon in our austenite. We're increasing the local carbon concentration above the bulk carbon concentration by a given amount each lath. And eventually that local carbon concentration is going to hit that T0 value. And at that point, nucleation of the bainite sublaths are going to stop. if the nucleation mechanism is completely diffusionless. Right? This is not necessarily a simple concept. Right? So we're going to hit this again on Monday because I know people are going to be confused about it still. Right? So as we lower the temperature, we shift this T naught goes to higher temperatures, right? And I mean higher carbon concentration as we lower the temperature. And that's what gives us the shape of this bainite, the amount of bainite that forms at a given temperature, right? It's how far over we can shift that T naught curve. Right? If we can shift it over far enough that if we go to all bainite, we don't ever exceed the T naught composition, then we'll get 100% transformation. If we're somewhere in between, we're going to eventually hit it and stop, right? And experimentally, what we should see then is that our carbon concentration in the austenite, right, should all follow the T naught line. And experimentally, this is what we see. So we can, I would say there is a general consensus, right? And anytime that there is a general consensus, it means there is a strong minority, right? A vocal minority who believes otherwise, that the nucleation of bainite is diffusionless, right? Based on this, I think this is pretty compelling experimental evidence. But there are people who find things to disagree with, right? And people who do a lot more steel work than I do. So, right, my opinion is not the be all and end all of the discussion. So we will revisit that on Monday and finish off bainite.